Tackling Food Insecurity, Machine Learning for Virginia. Many people lack reliable access to affordable and nutritious foods. Food insecurity is a serious problem in Virginia and across the country, with far-reaching implications for the health and well-being of those affected. In 2018, 842,870 Virginians, or an estimated 9.9% of the population, were considered food insecure. The COVID-19 crisis has had a devastating impact on food access. In 2020, the level of food insecurity in Virginia is estimated to have more than doubled to almost 22.5% at the height of the pandemic. We wanted to study the data in the USDA's Food Atlas to help come up with solutions. The dataset contains county and state level data from across the United States for factors related to food access as well as geographic and demographic data. So our goal for the project was to use machine learning techniques like regression analysis and k-means clustering to identify factors associated with or that might contribute to food insecurity in Virginia.
The first thing we did as part of this project was to generate visualizations of our data. The label we're going to be predicting is population percentage with low access to grocery stores, and all that data is from 2015. So we simply plotted that feature against the latitude and longitude to get maps of the United States and Virginia. You can see both of those up there respectively. With Virginia in particular, it's nice to note that most communities in Virginia are going to have high access to grocery stores, but those red and yellow dots indicate areas where there's significantly lower access. In terms of data cleaning, it was pretty easy. You can see on the left, our data set was composed of a bunch of CSVs, so the first step was to merge those all together. Then through feature engineering, we created an XGEF feature called population density, which we found to have a high correlation with our label. Then we dropped messy columns that were missing too much data. We dropped categorical features that were just names of counties and states and wouldn't help with predictions. Finally, we separated our labels and transformed all our data through the pipeline right there. Pretty simple pipeline, but it was effective for this instance because all we had was numerical data to transform. Finally, we used that data to train 4 regression models. We trained a linear regressor, a ridge regressor, a decision tree regressor, and a random forest regressor. And that score there represents the mean RMSE when they were trained with tenfold cross-validation. The random forest clearly had the lowest error, so we decided to go ahead with that. And after hyperparameter tuning with grid search, it actually didn't change, which indicates that we already had optimal hyperparameters, which no problem there, just less work for us to do. As a result of all of our regression, we obtained a model which is able to predict low access percentage population to grocery stores with an RMSE of about 14.2. And you can look in that graph on the right. It's a pretty strong correlation between our predicted and actual, which is exactly what you'd expect and hope for. And as I said, the RMSE is 14.2, but average error is actually going to be a little lower in most cases due to the fact that RMSE is sensitive to outliers, and we have quite a few outliers up here at the top right of our data. At this point, our model is ready to be implemented, and if this were a real project, we would deploy it, and the government could use it to predict at-risk communities and supply them with necessary aid.
Rather than trying to further improve our regression models to predict future values of low access to grocery stores, we pivoted to use an unsupervised learning method, k-means clustering. We used the ELBA method and a useful Python package called need to find the optimal cluster amount for our dataset, which is 4. Once our dataset was divided into 4 clusters, we found features that were the most different between groups using their standard deviations. We then plotted the mean value of these features for all clusters to find the characteristics that define each group and how they differ from each other. We found that cluster group 0 included the least amount of counties in Virginia, which were Arlington, Fairfax, Virginia Beach, Richmond, and a few others. Members of this group had high counts of grocery stores, farmers markets, and stores that accepted food stamps. Counties in this group also had higher population sizes. Cluster Group 2 had the highest counts of farms, food hubs, and slaughterhouses, which included places like Floyd, Frederick, Albemarle, and Shenandoah. From our findings, we saw that Group 0 and 2 are not at risk to low access to food. Cluster Groups 1 and 3 were harder to differentiate. Charlottesville, Danville, Fredericksburg, and Madison were some of the places included in these 2 groups. Members of these groups have fewer grocery stores, higher rates of poverty, and higher counts of children that qualify for free lunch at schools. Overall, we found that these 2 groups were the highest risk for food insecurity. Our findings show that k-means expose locations in Virginia that have low access to food. For example, looking at the counts of SNAP-authorized stores in Virginia, which are stores that accept food stamps, we can see that Cluster Group 0 has the highest count. This can be attributed to the higher population sizes of the counties in Cluster Group 0. However, when the ratio of food stamp redemptions over the number of stores that accept food stamps, we see that Cluster Group 3, one of our high-risk groups, is the highest, demonstrating a real problem rather than something caused by difference in population density. Another concern is that we expected to see big differences in the percent of the population that had low access to food across these groups. Instead, we found that this value was fairly consistent, meaning if the USDA considers this an important metric in determining which communities are high priority in improving food security, it is not encapsulating the differences we were able to see through cluster analysis. Through using K-means, we were able to specifically pinpoint where in Virginia food insecurity is a problem and demonstrate ways in which we can improve low access to food across these counties. We also were able to point out that the metric used to define low access to food should not be the only measurement used to characterize a location as food insecure.